All right, so we're going to look at a very typical problem, and this is basically what you guys did, except the difference is the student's going to throw the object and catch it at the same height. So one thing that we can do here is say that that launch height is going to be y equals 0. So instead of measuring from the ground, we're going to measure from the launch point. And the velocity is going to be 15 meters per second upward. And the first thing we want to do is draw a motion map. So if I'm thinking about launch occurring like right here, if a little bit of time passes at first, the ball is going to go a pretty good distance because you threw it fast. And you guys probably really noticed in the video analysis as the ball moved upward, your points get closer and closer together. And then maybe near the top, it only moves a little bit because it's going pretty slowly as it reaches that turnaround point. And then if I do this with some symmetry, on the way back down, it's actually going to also be symmetric as it falls. Each one of these is kind of maybe 10 frames if you want to think about it like that. And then if we're to add some velocity vectors, we're going to have a lot of velocity at launch. So this is kind of our t equals 0 seconds here. As it rises, it slows down, so the velocity vector is going to get shorter in each case here on the way up. So slowing down, velocity gets less and less. And then right at the top, if we got that exact instant where it turns around, the velocity is 0 at the peak. And that's something that we'll use in some problem solving. Okay. On the way back down, again, there's going to be symmetry. So on the way back down, it's moving downward with the same speed it would have had on the way up. So I'm going to try to make that vector the same length, just downward. These two vectors would be the same. As it falls, it's gaining speed at the same rate that it lost speed on the way up. So again, these two vectors should be fairly similar in length. Same thing here. Here it's picked up a good bit of speed downward. So I'm trying to make these two vectors the same length. And then right before you catch it, if you catch it at the same height, it's going to be moving downward with the same amount of speed as it did at launch. So that symmetry is going to help us in our analysis. So what we saw in the graphs is your graphs kind of started at a positive height because we measured from the ground. But if we measure from launch point, we're going to see that parabola shape in the position graph with the peak up here. The velocity graph started positive because we launched it. In this case, we would even know that that launch speed was 15 meters per second, as it's given in the problem. And again, it slows down steadily and then turns around. There's a moment where the velocity is 0, and then it speeds up in the negative direction. In our motion map, on the way up, it's moving up, but it's slowing down. So the acceleration is downward for the first half of the flight. And then on the way back down, the velocity is increasing downward, so the acceleration is still downward. What I'm saying is the acceleration is never upward. Even though some of the motion is upward, the acceleration is always in the downward direction. So this acceleration we would expect to be steady and negative, and specifically at negative 9.8 meters per second per second. So we didn't graph that in the lab, but that's what the acceleration graph would have looked like. All right, any questions at that point? Okay, so next we want to build our equations from the general equations. And so I'm going to go ahead and write in the general form of the equation first, 1/2 at squared plus initial velocity times time plus initial height, we call that y0. Now, if we launch from height 0, y0 is 0. It's going to go away from the equation. The t-squared coefficient should be half the acceleration, well, half of g, half of the acceleration due to gravity. We could either write it as 1/2 times -9.8, or I'm just going to go ahead and take half of it, which is what we saw in the investigation pretty closely. That's 1/2 a times t squared. Here, the initial velocity was given as that positive 15 meters per second. So I know this term. And again, we did see that in the investigation as well. You guys threw it 7 or 8 meters per second in the upward direction to start. So with this equation, I can plug in any time and I can locate the position, right? Any time along there would be locating the y or the position. So maybe I'll just, so we're sure on it, we're talking about y. The general velocity graph is acceleration times time plus starting velocity. And this is not half the acceleration, this is the acceleration. So in this case, I expect this one to be -9.8. I could put a 0 on there if I wanted to. Meters per second, or meters per second squared, times t. And here, I do have an initial velocity. It was that 15 meters per second. And it's not multiplied by anything. It's just our intercept, our starting point. And then the acceleration is just a steady -9.8 meters per second. It does not change. All right, so those of you that know some calculus, you might notice that if I take the derivative of this equation, okay, so if I take the derivative of this, I get the velocity equation. To take a derivative, you take the exponent times the coefficient, and then you drop the order of the coefficient by 1. If you don't know that yet, it's not going to mean much to you. But the velocity equation is the derivative of the position equation, and then if I took the derivative of the velocity equation, it is the acceleration equation. You don't need to know that to understand these equations, but that can help. All right, so we've got not much time left, right? So let's just talk about how we might approach this problem. And then what I would say is try to finish out the rest of the problems on this sheet for Monday, right? I'll see you Monday online. So if I want to know how long it takes to reach its peak, what I actually use is the velocity equation. And I'm going to use this hint that the velocity is 0 at the peak. Okay, so I'm going to pull down the velocity equation. I know it equals, and I'm going to write it without units to make it a bit simpler. This was the acceleration. This was the starting velocity. What I want to know is the time when the velocity is 0. So I can set this equation equal to 0. I could do it over here as well and solve for t. That's going to tell me how long it takes to reach the peak. So my algebra, right, I'm going to subtract 15 from each side. I need to divide through by negative 9.8, both sides, to solve for t. This would be the time it takes to reach position 0. And that comes out to be 1.53 seconds. And that would be, again, how long it takes to reach the peak. So now I know at the peak, my time is 1.53 seconds. That's how long it takes to get to that peak point. A typical follow-up question would be, calculate the height. Height is talking about position. So we had y equals negative 4.9 t squared plus 15 t. That was the starting velocity. The starting position we just said is 0, so we don't need to solve that one. To find the height at peak, I would want to plug in the peak time, 1.53. I need to square it. I would also plug it in for t. That will give you the peak height. You can check it for yourself, but it should come out to be 11.5 meters. Okay. So there are a couple of follow-up questions on the back that analyze what happens next to drop back down. How much time is that going to take? And then proving the velocity also. See if you can do that for Monday, but we'll leave it at that for today. Let's go ahead and take care of desks.